Welcome back to the Explainer. So last time we met John Dalton's atom, right? This idea of a simple, indivisible little sphere. And this idea was huge. It really laid the groundwork for all of modern chemistry. But, like any great idea, it also brought up some really big new questions. I mean, if these things are real, how do we even begin to describe them? Or measure them? Well, in this Explainer, we're going to dig into the seriously clever tools chemists came up with to do exactly that. So here's the plan. We're going to start by building the alphabet of chemistry. Then we'll tackle how to weigh something you can't see. After that, we'll look at how atoms hang out in the real world. And finally, we'll learn how to write their recipes. Let's get into it. Okay, first things first. Scientists needed a way to talk to each other. A universal way to represent all the different kinds of atoms. The elements. John Dalton actually created his own set of symbols. Kind of like chemical hieroglyphics. And they were a really great start. But you can probably see the problem. As we discovered more and more elements, trying to remember a unique picture for every single one, it got messy, fast. And then this chemist named Berzelius came along with a much, much simpler idea. He said, hey, why don't we just use letters from the element's name? And honestly, it was a total game changer. It was systematic, it could grow as we found new elements, and boom, suddenly chemists all over the world were speaking the same language. And that's pretty much the system we use today, standardized by what's called the IUPAC. The rules are super simple, 1 or 2 letters. First one's always uppercase, second one's always lowercase. And sometimes, for a little bit of fun, the symbol comes from an old Latin name, which is why iron is Fe, from the Latin ferrum. Pretty cool, right? It gives us this perfect global language for chemistry. So great, we've got a language to name all the atoms, but that just leads us to the next massive challenge. Now that we can write H for hydrogen, how much does one tiny atom of it actually weigh? And this was a huge problem. I mean, think about it. Weighing a single atom directly? No way. That was completely impossible back then. So scientists came up with this really elegant workaround. They thought, okay, what if we don't find its actual weight? What if we just weigh it relative to something else? And that's exactly what they did. They picked a common atom, carbon-12, and they just decided. They said, this atom has a mass of exactly 12 atomic mass units. So our new unit of weight, the atomic mass unit, or U, is literally just 1/12 the mass of a single carbon-12 atom. Everything else is measured against that. Let me make this super clear. Imagine you're a fruit seller, but you don't have any standard weights. So you grab a watermelon, and you declare, this watermelon weighs 12 units. Then you cut it into 12 identical slices. So each slice is now 1 unit, right? Now you can weigh everything else. An apple might balance 1 slice. A pineapple might balance 16 slices. That's exactly how relative atomic mass works. The watermelon is carbon-12, and the slices are our atomic mass units. And when we use this system, we find out that a hydrogen atom weighs about the same as one of our slices. So its mass is 1U. An oxygen atom is heavier. It's like 16 of those slices, so its mass is 16U. All of a sudden, we had a really practical way to compare how heavy different atoms were. Okay, so we've got symbols and we've got weights. We're building a pretty good toolkit. But here's the thing. In nature, atoms almost never travel alone. They aren't exactly lone wolves. No, they're actually really social particles. They bond together, they clump together in massive, massive numbers to form all the stuff that we can actually see and feel and touch. And they tend to group up in 2 main ways. First, they can form these electrically neutral partnerships called molecules. Think of a water molecule, H2O. That's a little team of atoms sticking together. Or atoms can gain or lose electrons, which gives them an electrical charge. We call these charged atoms ions. A perfect example is table salt, which is made of positive sodium ions and negative chloride ions. So that brings us to the final piece of the puzzle for today. How do we actually write the recipe, the chemical formula, for any of these compounds? Well, the secret ingredient here is a concept called valency. You can just think of valency as an atom's combining power. Or even better, think of it as how many arms an atom has to link up with other atoms. The octopus analogy here is perfect. If an octopus has 8 arms, a valency of 8, it could hold hands perfectly with 4 humans who each have 2 arms, a valency of 2. Now, to actually use valency, chemists came up with this awesome little trick called the crisscross method. It's a super simple set of steps that lets you figure out the exact ratio of atoms you need for a compound. Let's just do one together. Say we want the formula for aluminum oxide. Okay, we write the symbols Al and O. We know aluminum has a valency of 3 and oxygen has a valency of 2. Then you just crisscross those numbers. The 3 from the aluminum goes down next to the oxygen, and the 2 from the oxygen goes down next to the aluminum. And there it is. The formula is Al2O3. Simple as that. All right, let's step back for a second and just quickly recap the amazing tools we've just added to our chemist's toolkit. I mean, think about how far we've come. We went from just the basic idea of an atom to having a universal language of symbols to write them down. We figured out a clever way to weigh them using a relative scale. We understand that they hang out as either molecules or ions. And now, we even have the rules of valency to write the recipes for pretty much any simple chemical compound. Which, of course, brings us to one last really interesting question. We now know how to write the recipe for water, H2O, and we know the relative weight of one H atom and one O atom. But what about the whole molecule? How much does the entire finished dish weigh? Well, we're going to tackle that and a whole lot more in part 3. See you then.